Hello everybody, welcome to my channel. This is my series Cracking LeetCode from Scratch, episode 1, which is also the first problem on LeetCode. This video aims to have acquaintance with algorithm. By solving this problem, clearly we can see different algorithms we choose lead to different execution efficiencies. First, let's look at what is an algorithm. According to Wikipedia, an algorithm is a finite sequence of mathematically rigorous instructions, typically used to solve a class of specific problems. And also, it says, as an effective method, an algorithm can be expressed within a finite amount of space and time. So, sum it up, we got 2 points. The first is an algorithm is a method to solve a problem. Normally, there's more than one method. Which one should we choose? Of course, we choose one that costs less time and uses less spaces. Or more professionally speaking, we choose the algorithm with low time complexity and low space complexity. Generally, in real world, we can't have both. We choose one of them over the other. During the development of computer science, both sides have the best applications. For example, cache system. Cache system uses more space to get faster operation, which chooses time over space. On the other side, virtual memory in OS aims to expand memory spaces the process can use at the cost of more CPU clocks, which chooses space over time. About these two examples, we won't dig it up here. If you are interested, Google it more for details. Okay, let's get back to LeetCode. For most problems on LeetCode, we can't have both. So LeetCode prefers time over space. That is, if you can find an algorithm that costs less time but uses more spaces, which we take as a better algorithm. While nothing is absolute, for some problems on LeetCode, we do be able to find an algorithm with low time and space complexity. I believe we'll run into some in future. Okay? Next, let's solve this problem 1 to sum. Here we got 2 algorithms and 3 implementations. Before any of this, let's break down the problem first. The problem says, given an array of integers nums and an integer target, return indices of the two numbers such that they add up to target. That is, finding two numbers from the array and the sum of the two numbers equals target. And also it mentions each input have exactly one solution, and you may not use the same element twice. What does this mean? Let's look at the example 2. The input array nums equals 3 to 4, and the target equals 6. So return 1, 2. That is 2 plus 4 equals 6. But we can't return 0, 0. Otherwise, the element 3 will be used twice, which is not allowed by this problem. This is an easy problem. It is easy. Searching two numbers from the array can just be solved by using nested loops, which is the first algorithm, brute force with nested loops. A little attention here. The inner loop starts from I plus 1 to make sure two numbers. And the loop body is simple. Just check if nums I plus nums j equals target. If it does, return the indices array ij. Finally, the return statement will never be reached because each input has one solution. Okay, about time complexity. Obviously, this algorithm nested two loops, so it is O(n) squared. As to space complexity, there's one thing I should point out. When calculating space complexity, only memory spaces allocated during the execution of the algorithm will be taken into account, while The spaces taken by input params and returned results will be ignored. For this algorithm, the spaces for input array nums, target, and the returned indices array ij will be ignored. Only a couple of local variables n, I, j during the execution of this algorithm will be taken into account. So the space complexity is O1, or we can call it constant space. Okay, we did it. But one question. At the first time you submitted successfully, aren't you excited a little? I must say, sure I am. But soon we found one frustrating thing. Our submissions of this algorithm rank in the tail section of all the submissions, which tells us there must be something we can do to make our algorithm better. Okay, this is a searching problem. We fixing one number in the outer loop and searching the other in the inner loop. So we should focus on how to accelerate the searching process. As for searching, the best and fastest way is using hash table, which is our algorithm 2, using hash table. This implementation iterates twice over the integer array nums. The first iteration puts all the elements into the hash table, and the second iteration fixes one number num and then search the hash table for the other number target minus num. If it exists and it's different from num, then return the indices I and j. Next, let's take an example to see how this runs. Given nums equals 5, 2, 3, 2, and target equals 4. The first iteration puts all the elements into the hash table, but there's one thing about element 2. Originally, there are two 2's with index 1 and index 3. At the end of this iteration, the index 1 was covered by index 3. Then let's do the second iteration. First element 5 with index 0, and we need 4 minus 5 equals minus 1. Obviously, minus 1 isn't in the hash table, so continue. And the second element, 2 with index 1, we need 4 minus 2 equals 2. And there is 2 in the hash table with index 3, and it meets the condition I doesn't equal j. So return the final results, 1, 3. About time complexity, there are two iterations. The first uses on and the second uses on. So sum them up, we get O2n. But normally, if there is a constant before n, we still take it as on. Here O1 represents the time that is used by putting in and getting from the hash table. And the space complexity, obviously, during the execution of this implementation, the extra space hash table was allocated to store all the elements of nums. So the space complexity is on. This implementation iterates twice. Actually, we can incorporate these two iterations into one. Then we get the second implementation. The core procedure of this implementation is fixing one number num and search the hash table for the other number target minus num. If it exists, then return the indices I, j. If it doesn't, put the num into the hash table. Next, let's take the same example to see how this runs. The initial state of a hash table is empty. Then let's do the iteration. The first element 5 with index 0. We need 4 minus 5 equals minus 1. Obviously, minus 1 isn't in the hash table, so we put 5 with index 0 into the hash table. And the second element, 2, we need 4 minus 2 equals 2. 2 isn't in the hash table either, so we put the second element 2 with index 1 into the hash table. And similarly, we put the third element 3 with index 2 into the hash table. And then the last element 2 with index 3. We need 4 minus 2 equals 2. Great, we got 2 from the hash table with index 1, so we return the final results 3, 1. Till now, the two implementations aren't exactly the same. This returns 3, 1, and the other returns 1, 3. The results are reversed. How's the difference? Attention, you guys, listen carefully. Given integer array contains a, b, and a plus b equals target c. For the first implementation, we iterate at a and search the hash table for b, then return ab. But for the second, we iterate at b and search the hash table for a, so return ba. That's the difference. And the time complexity and the space complexity are obvious, or ON. This is algorithm 2 using hash table. As we've known, this is a searching problem. Besides algorithm 1 brute force and algorithm 2 using hash table, is there another way to solve searching problem? Yes, there is, and that is binary search. So first question, for this problem, does binary search work? The answer is no, because binary search requires the input array is sorted, while for this problem, the given input array is unsorted. You may say, can we sort it first? The answer still be no, because this problem requires to return the indices of the two problems. If we sort it first, the original location or the original indices will be changed. Most likely, you still can't return the right answer. So how can we use it? If you really want to use binary search, please refer to LeetCode problem 167 to sum 2. Input array is sorted. Okay? Next, let's do some conclusion and reflection. From the first chart of this slide, we can clearly say different algorithms lead to different execution efficiencies. For this problem, the difference is big, nearly 10 times. And the second chart shows difference between two implementations of algorithm 2. At last, here's a little question. About the two implementations, why doesn't the second implementation need I not equal j? If you got some, please comment below. I really appreciate it. Alright, thank you for watching, guys. If you like this video, please give me a thumb up and hit the subscribe button. See you next time. Bye.